Welcome everyone. I'm excited to kick off this presentation on master AC refrigerant charging. Today, we'll be exploring a complete field guide for R22, R410A, R134A, and R407C, especially for hot climates. Over the next few slides, we'll cover key techniques, best practices, and tips to ensure your refrigerant charging is safe and efficient. Let's get started. Let's start with safety first. It's essential to always wear gloves and goggles to protect yourself during the process. Ensuring proper ventilation in the work area is also critical to avoid any buildup of fumes or gases. Remember, never use oxygen or air for testing purposes, as this can be dangerous and lead to accidents. Now, moving on to the required equipment. You'll need a R410A manifold rated for 800-5000 sig, a scale that can measure within plus or minus 10 grams, and a micron gauge capable of measuring down to 500 microns or less. These tools are vital for accurate and safe system servicing. Next, there's a critical check you must perform. Always identify the metering device, whether it's a TXV or a fixed orifice. This step is crucial because it determines the charging method you'll use. Proper identification ensures you're following the correct procedures for the specific system you're working on. Connecting all these points, safety and proper equipment use, are the foundation of a successful and safe service process. Ensuring you follow these guidelines helps protect you and guarantees the system is serviced accurately. Let's take a closer look at the target pressures and temperatures involved in comfort cooling applications. The evaporating temperature, or SSD, typically ranges between 5 to 7 degrees Celsius. This is the temperature at which the refrigerant absorbs heat from the space we're cooling. On the other hand, the condensing temperature, or SCT, is around plus 15 degrees Celsius. This temperature is influenced by the ambient conditions, which in the Saudi climate can be about 12 to 20 degrees Kelvin above the ambient temperature. It's important to understand that to analyze or design these systems, we convert the SSD and SCT into their corresponding pressures, suction pressure and discharge pressure, using the refrigerant's pressure-temperature chart. This step is crucial because it allows us to accurately determine the operating pressures based on these temperatures. By understanding these target pressures and temperatures, we can optimize the system for efficiency and reliability in providing comfortable cooling, even under challenging environmental conditions. Let's walk through the 7-step charging workflow to ensure a proper and efficient system recharge. First, we start with identifying and recovering the existing refrigerant. It's crucial to confirm the type of refrigerant we're working with, check the metering device, and recover the old charge completely before proceeding. Next, we perform a pressure test. For R22 and R134A, we aim for pressures between 150 and 200 sig, while for R407C and R410A, the range is typically 300 to 400 sig, using nitrogen to pressurize and check for leaks. Then, we evacuate the system. Our goal here is to reach a vacuum of 500 microns or less, and hold that vacuum for at least 10 minutes to ensure the system is dry and free of moisture or non-condensables. After that, we weigh in the new refrigerant charge. For blends, we typically add 80 to 100% of the nameplate charge into the liquid line, while for single-component refrigerants, we can add it as vapor. Accurate weighing is key to proper system performance. The 5th step is running the system in cool mode for about 10 to 15 minutes to allow the refrigerant to stabilize. During this time, the system should settle into a steady state, ensuring proper oil return and system operation. Next, we fine-tune the charge. For systems with a TXV, we check the subcooling, aiming for about 5 to 12 Kelvin. For fixed orifice systems, we focus on superheat, targeting 8 to 12 Kelvin. This step ensures optimal performance and efficiency. Finally, we perform a final verification. We check system pressures, superheat or subcooling, compressor current, the site glass, and overall system performance. This comprehensive check confirms everything is operating correctly before we finish. Following this systematic workflow helps us achieve a reliable, efficient, and long-lasting system. Let's talk about the TXV systems and the subcooling method. The target subcooling range is typically between 5 and 12 Kelvin, but it's always best to check the nameplate for the specific system. Now, if you notice the subcooling is on the low side, meaning below 5 Kelvin, you should add liquid slowly to the liquid line. This helps increase the subcooling and ensures proper system operation. On the other hand, if the subcooling is too high, above 12 Kelvin, you might need to recover a small amount of charge from the system. This prevents overcharging and maintains efficiency. The key formula here is simple. Subcooling equals the saturation temperature of the liquid minus the temperature of the liquid leaving the TXV. So, by monitoring these temperatures, you can make precise adjustments to optimize performance. Overall, understanding and controlling subcooling is essential for maintaining the right refrigerant charge and ensuring your system runs smoothly and efficiently. Let's talk about the fixed orifice superheat method and how to determine the target range. Typically, a normal superheat reading is between 8 and 12 Kelvin. However, under high load conditions, it's acceptable to see a slightly lower superheat, around 5 to 9 Kelvin. Now, if you notice a superheat that's higher than the normal range, it indicates a starved system, meaning there's not enough vapor entering the compressor. In this case, you should add vapor slowly into the suction line to bring the superheat back to the target range. Conversely, if the superheat is too low, suggesting flooding, you need to recover some of the charge carefully. This helps prevent liquid refrigerant from reaching the compressor, which can cause damage. Remember, the key formula here is superheat equals the temperature at the outlet of the suction line minus the saturation temperature of the evaporator. This calculation helps you accurately gauge the system's status and make appropriate adjustments. Understanding and controlling superheat is crucial for efficient system operation and longevity. So keep these ranges and adjustments in mind as part of your overall maintenance strategy. Let's take a look at some important adjustments we need to consider during hot weather conditions. First, the high ambient impact. When the outdoor temperature hits around 46 degrees Celsius, we can expect the saturated condenser temperature, or SCT, to rise to about 61 degrees Celsius, which is roughly 15 Kelvin higher. This increase means we should anticipate higher discharge pressures from the system, so keeping an eye on those pressures is essential. Next, system cleanliness becomes even more critical in these conditions. Ensuring that the condenser is clean and that the fans are operating at full speed helps us get the most accurate readings. Dirty condensers or sluggish fans can give us misleading data, which can lead to improper adjustments or system inefficiencies. Finally, airflow requirements play a key role. For example, approximately 400 CFM per ton of cooling is needed, so for a 20-ton system, that's about 8,000 CFM. When airflow drops below this level, it can distort pressure readings and impact overall system performance. Maintaining proper airflow is crucial, especially in hot weather, to ensure the system operates efficiently and reliably. Connecting all these points, during high temperatures, paying close attention to ambient impact, maintaining cleanliness, and ensuring adequate airflow are vital steps to keep the system running smoothly. These adjustments help us prevent potential issues and optimize performance under extreme conditions. Let's take a quick look at all the refrigerants listed here, starting with R22, which is a common older refrigerant. Its suction pressure is around 75 sig, and the discharge pressure ranges from approximately 275 to 285 sig. It typically uses mineral or ob oils, and we usually charge it with vapor, often for topping off systems. Moving on to R410A, which is more modern. Its suction pressure is about 130 sig, with discharge pressures between 430 and 470 sig. It requires POE oil and is charged as a liquid only. Next, R134A has a lower suction pressure of roughly 35 sig and a discharge pressure around 190 to 210 sig. It uses POE or PAG oils, and we top off systems with vapor. Finally, R407C has a suction pressure in the range of 95 to 105 sig, and its discharge pressure is between 290 and 320 sig. It uses POE or OB oils and is charged as a liquid only. The key takeaway here is that each refrigerant has different pressure ranges, oil requirements, and charging methods. Sharing this quick reference with your HVAC team helps ensure everyone is on the same page about these important details, which is essential for safe and efficient system operation.